So, good evening. Today we'll do the week 6 problem solving and doubt clearing session. And this will be the outline for today's presentation and doubt clearing session. I will first touch upon the different types of ADC, why we use a ADC, why we use a DAC, and some of the types and some of the working. I will just briefly recap the important ADCs. Next, I will talk about the current sensing circuits, where what are the various types of current sensing methods that are available, as well as I will talk about the various types of current sensing methods which are available in the circuits, as well as the various types of current sensing, low side, high side, or complete current sensing, etc. Then we will talk a bit of the ADC and DAC, the drivers which are required for them. Then we will talk about the gate driver. So the gate driver is used for turning on the MOSFETs. So the MOSFET just cannot turn on by giving a PWM signal. They have to be driven by a gate driver which has sufficient capability to charge the MOSFET, etc. So that's why about gate drivers we will study, about also the bootstrap capacitance arrangement, etc. We'll go through. Then about the sensing circuits which are used in the board. So these are with respect to the components which we have, has been used in the hardware demonstration board used for this course. Then also I will be showing some of the board schematics will be shown, and then we will proceed. So do you guys have any topic on which you want me to focus a lot, or anything on which you have lots of doubts?
Sir, I'm having a doubt whether zero order hold is used as an ADC or DAC, sir.
For the MATLAB thing,
Yes, sir.
in MATLAB we are using the zero order hold for the ADC part.
Okay, like zero order hold is for for DAC. Is there any simple circuit like that?
Okay, in the MATLAB simulation we are not using any specific block for DAC, because
Okay.
in MATLAB, like I'll just show you. Okay, so if you can see this, right?
Yes.
So in MATLAB, what we're doing, we have a ADC, is sampling. Then we have the controller GC of Z, and that generates, suppose your I reference of N. And then directly we are passing it on to the comparator in MATLAB. Okay. This we are doing in MATLAB. Why? Because this I in the real, this I reference of N is just an integer. Okay, it is just an integer. And this IL also is like our, double data type. IL of N is also a double data type. This also is actually our double data type. So they are, analog values. They are not actually digital values in MATLAB. Because when MATLAB is running, okay, let me just talk about real world example, or in the real world hardware board. Suppose the voltage signal over here is 3 volt. When the ADC converts it, it will represent it in a series of 1, 1, 0, 1, 1, 0, 1, 0, etc. Okay. Then my digital control system will represent it in terms of like the I reference of, and it will represent as 0, 1, 0, 1, 1, 0, 1, 0, etc. Then to convert this value, we use a DAC to convert it into form of like around 2.5 volt, etc. But in MATLAB, we don't do this. In MATLAB, this is not this signal is not getting converted to this form, and this also is still not getting converted. It's still not in a binary form. It is still in a digital form. So MATLAB is 3 volt. It still remains 3 volt. This converts into 2.5 volt, and so we do not have a requirement for DAC in MATLAB simulations, which Sir has shown. Hello. Vinarji, are you there? I didn't hear actually. Okay, so anyway, so
Sir,
yes, tell.
sir, yeah, it is okay, sir. Then
Mm-hmm.
is
Okay.
there anyone speaking, sir? I can't hear anyone speaking.
Okay, yeah, that's good thing. Okay, so we'll proceed. So in the real world, when we are doing the practical board, in the practical board, we require an ADC. The ADC will convert this analog value into some digital data form. There are various ways of representing them, and based on the ADC, the configuration, etc., it will represent it in some format. And that, and we must know which format it is represented it in. And then in the digital control system, we will use our PI controller or any other sort of blocks of code which we have written. And this digital control system could be a microcontroller, it could also be an FPGA, etc. So these will generate a reference value. It could be a current reference, it could also be this PWM reference, etc. Both any of this it can generate, and that we'll convert it using a DAC so that it could be used to actuate it. So there is not, the DAC may not always be required because it could also just generate a gate signal Q. Okay, the gate signal Q also is a digital thing. So the gate signal Q goes via a gate driver, and that is our, this is my gate signal Q, and it goes via gate driver to my MOSFET. Okay, so this is my input to the MOSFET. So this will turn on the MOSFET. Okay, so if this is the case, if so
Sir,
DAC is
this queue is okay. Like
Mhm.
I thought that the queue and the like other signal you are showing is different.
Which other signal?
You are saying that queue is same as that pulse, right?
Yeah, yeah,
Okay, okay,
yeah. It's the same
okay.
in phase everything. So Q may be like 3.3 volt. This would be like around 10, 12 volt or something. Because this
Okay.
level should be, this gate to source voltage should be greater than your threshold voltage of the MOSFET for the MOSFET to turn on. Okay. So that when we be discussing of the gate driver, I'll talk about it further. Yeah. So next I'll continue. Okay, so this is my ADC. It will take an analog signal, which is a continuous time signal, and it will convert into a digital vector. Okay, digital vector, because it is in discrete time, it has many bits, etc. So what is the resolution? So the ADC can be of 8-bit, it can be of 10-bit, etc. That determines the resolution. So this ADC will have a sort of input voltage. Say suppose the input voltage of the ADC, like the supply voltage to the ADC is 3 volt. Okay. So, and suppose it was an 8-bit ADC. So the resolution of the ADC will be equal to 3 upon 2 raised to 8. Can anyone do the calculations and tell what will be the result?
No, it is 0.0117.
0.0117. So approximately the resolution is 11.75 millivolt. Okay. So such a small change in voltage the ADC can detect. Suppose my voltage signal, the V of T was like this. Okay, it was varying like this, assume. So between this and this, if this gap is less than 11.75 millivolt, then the output will remain the same. Okay, suppose this was, let us say this was suppose this was 0 volt. Okay, and this is around 10 millivolt. So initially the output of the ADC will be 0, 0, 0, 0. And here also the output of the ADC will be 0, 0, 0. So this resolution is only when this becomes this upper bar, this B becomes more than 11.75 millivolt, then only this ADC's output will change from 0 to 1. Okay, so that is like in the scale. Like if we have a scale, assume this is our scale, the 0, 1 centimeter, and there are 10 dashes. Okay, so those dashes are like 0.1 centimeter, 0.2 centimeter, etc. So the minimum value which we can measure using the scale distance is 0.1 centimeter. Similarly, for the ADC, the minimum change which it can detect is known as the resolution of the ADC.
Sir, this V supply is entirely different from the analog signal, right?
Yeah. This is like a biasing supply for the ADC.
Okay. You are saying, sir, if the V supply I am giving just 2 volts, if it is rated for 3 volts and I'm just giving only 2 volts,
Okay.
then will the resolution changes?
Yeah, if the resolution will decrease further, no? No, if listen, why we give this 3 volt? If it is referred to a ground, okay, we supply is 3 volt. That means the ADC can accept signals at the input, which is only between 0 to 3 volt. Okay, the range, the signal V of t should lie between 0 to 3 volt. If it is 3.3 volt, then my ADC will still give 1, 1, 1. Okay, it'll still give all high. And it might also damage the ADC. So that we have to take into account. So if we want the ADC to accurately convert the analog input to a digital output, then the input signal applied to the ADC must be less than the supply voltage to the ADC.
Okay, sir.
Yes. So that's the thing. Then another thing is the sampling rate of the ADC. How fast we want the ADC to take samples. So we will give a clock signal. Okay, we will give a clock signal to the ADC. And once we give the clock signal to the ADC, then it will sample, it will convert, etc. And the output will be available over here. Okay, the digital output will come. There will be a sort of delay. Okay, delay will be there. This delay is inherently there. Some ADCs have more delay, some ADCs have lesser delay. So usually parallel ADCs are very fast and serial ADCs are slower. But if we have parallel ADC, it will consume lots of power, and we require large number of transistors. It would be costly, etc. So there are various reasons depending on the type of application you use. You will choose the type of ADC, but the sampling rate is always there, and also there's a delay. And if we are using a high rate of sampling, then there'll be like a power will also be consumed. So the ADC will also consume some power, and it might, and if we want a very highly efficient converter, then we would require the power consumed by the ADC to be less, etc. So such things are there. Also, there will be a delay in the ADC for conversion time, etc. So now we will consider one type of ADC. This is known as the dual slope ADC. So in this ADC, what happens is, this is my input signal. Okay, this is my input signal, which I want to convert this V input signal to a digital value. Okay, to a digital value. And this is some minus Vref. It is some fixed bias voltage, etc. Something. So what do I do in the start? I apply this input voltage, and it passes through this integrator circuit. Okay. So this is my integrator circuit. And because it of the negative polarity, it will start reducing from 0. Okay, my output over here, this VC, it will start reducing from 0. It will start reducing at a rate given by minus Vin upon RC. It will reduce at that rate. And we let it reduce for a fixed time, T1. Okay, the fixed time T1 is nref into T. So nref is the number of these pulses, 1, 2, 3, 4, 5, etc. So that is fixed. It is some value nref. Okay. So for this nref time into T, which is the time duration. Okay, and this T is this time. The time between two pulses is T. So for this duration nref into T, my control this switch is at this part, and the input voltage is being sampled, and it is being integrated, and that's why it starts reducing at this rate, and that is for a fixed duration. After that fixed duration, what do I do? The control will come over here, okay, and instead minus VREF will be applied. Because of minus and minus, the slope becomes positive and it starts increasing, and it will increase like this, and it will at one instant it will touch 0. So when this VC becomes equal to 0, then what happens? It will detect it, okay, it will detect it, and that detection will come over here, and you will find out what was the number of what we say. Oh, sorry. Yes.
Sir, actually, instead of this V in and V minus V ref,
One
sir,
minute.
can you hear me, sir?
Yeah, I can hear. Yes, tell.
Instead of this V in and minus V ref,
Oh,
sir, why can't we write and putting minus here? Why can't we write this V in to be minus and V ref to be positive? I think this output of integrator will become negative, is it, sir?
yeah, see, this output VC is less than 0, no? This is 0 volt, and it is reducing like this.
No, sir. What I'm asking is, sir, this output of integrator will be the negative of input, is it, sir?
Yeah, negative input, yeah.
Okay, that's why we are, even though V in is positive, we are writing minus V in by RC.
Yeah, that is why. Because this minus sign, it is applied to the inverting terminal of the op-amp, right? That is why it is happening. That is why VC is reducing. And then if I apply negative voltage and to this negative inverting terminal, then it starts increasing. So what do I do is I will count these number of pulses. Okay, these number of pulses I will count. And based on what happens, how far it has fallen depends upon the magnitude of this input voltage which was applied. And then once it reaches 0, then I will tell the counter to stop counting and note down how much N it has taken. So this N is my digital equivalent of my V input. Okay, this N is a digital equivalent of my V input, and it is given by N ref into V in star upon V ref. Okay. So any doubts in this? See, this formula, how it has come is, this is a triangle, right? So by similarity, this is coming like this. This value is a fixed value. So we have V input star upon RC divided by N ref into T. That is equal to minus V ref, or just consider this magnitude V ref upon N into T. So T and T get cancelled, and this RC over here, this RC get cancelled. So we get N is equal to, there's something wrong. Using this we get, so this T and T get cancelled. So my N is equal to N ref into V in star upon V output. Okay. And this is a uniform clock, so this T remains the same. This T remains the same. The fixed duration remains the same. So one advantage of this is, even though this R can change, this C can change, this clock also there might be a jitter, this T also might change, but it is fairly accurate and it is tolerant against these changes. So that is why this dual slope ADC is used. Okay, so over here they've told the result doesn't reflect clock variation. So this T can change. Okay, suppose T is changing, then it will change for this time as well as for this time. So because it is because this N, as we have told, is given by V in into N ref upon V in upon V ref. Okay, so this N which is coming is independent of T. See, T is not in the equation, R also is not in the equation, C also is not in the equation. So it is only dependent on these values, and hence it is made independent of variations of R and C and T. They do not affect the digital output which comes out. Okay. So this is for the dual slope ADC. Then we will consider about the successive approximation resistor ADC, SAR ADC. So it works on the principle of binary search. Okay. So what happens is, yes.
Sir, in the last case in dual slope ADC, sir, can you tell after that how that V in is converted into digital?
Okay. So what happens
After that
is,
point?
yes, so now I get this value of N. Okay, I get this value of N. Assume it comes out to be 10 cycles. Okay, N comes out to be 10 cycles. All right. So if it comes out to be 10 cycles, that means the digital value is 10. The digital value of V in is 10. So when digital value of V in will be, suppose it will be written as 0. It is 0, wait, 0, 0. No, sorry, it will be 0, 1, 4 will be 0 and 1. So this will be the digital value of V in, if 10. Okay. This is, as we know that this is 2 raised to 0, this is 2 raised to 1, this is 2 raised to 2, and this is 2 raised to 3. So that is 8 plus 2 is equal to 10. So that is how this this value of the number of cycle gets converted into a digital number 1010. So you have any other question about that?
Sir, you can proceed.
Okay. Okay, Banerjee, you are not audible right now. Okay, Dharmaraj, actually N and NREF are not the same.
Hello.
NREF, yes.
Am I audible now?
Yeah, you're audible. Tell.
Sir, does this digital counter gives the number of clock cycles or the digital equivalent of the input voltage it gives?
It gives the digital equivalent of the input voltage as well as the number of clock cycles, right? Because the number of clock cycles is proportional to the input voltage applied. So there would be certain processes further to convert the number of clock cycles, convert the number of clock cycles to the digital value. Okay, that process is an internal part of the ADC that you don't need to be worried about.
If that is the case, like digital counter has gives the output of the number of equivalent clock cycles itself only, right?
Yes.
Okay. For converting this into our equivalent input voltage, there is another logic, which we
Which
are
one?
not going to discuss.
Which one? This one?
Yes, sir. From
No.
the digital counter, the output is N, right?
Yeah. Output is N, yes.
N is represented in the form of binary by the digital counter itself.
Yeah, it is represented by the form of the digital counter itself. Yeah.
Okay. For converting this to our equivalent V in star, there is another logic. Like we have to back calculate the V in from the V reference, right?
No, it is not like that. See, the digital counter is like a set of bits, right? It is like a set of bits, 1, 1, 0, 1, etc. So if this is 1, 1, 0, 1, it corresponds to like say 13. If this 1, 0, 1, 0, it corresponds to 10. So how does it work? The digital counter also has these number of bits, etc., and it will store it. Okay, and there would be further digital circuits, etc., to give it to show the output of the ADC when we want to require the ADC output. All these will be stored in certain registers, etc. So those things we will look into further. Right now, we are not interested in that.
I'm having doubt like whether the output of the digital counter is equivalent of the input voltage in digital format, or just the number of clock cycles in the digital format it is showing.
No, it is equal to the digital equivalent
Of input voltage.
Yeah.
From this we got just N, sir. Where the N is the output of which block here?
This one, no? B1, BN.
Then N is just the equivalent of the number of clock cycles, right?
Yeah. So this logic
This
says
is
that.
not.
No, see, suppose the value is, let us say this is a 3-bit ADC, okay? 3 bits.
Sir,
So it will
I'm
have,
having a question. I'll discuss that. Please give me 1 minute.
Okay. Okay, and yeah. And Dermira's NREF is not equal to N. Because NREF is a fixed value. You're giving a fixed NREF. You know NREF. Prior to your running it, NREF you know. NREF you know, VREF you know. So only V in star changes. And as V in star changes,
Here,
my N will automatically change.
the
Yes?
question is like this. V in star is 5 volts. N reference is 6. N reference is 6.
Okay.
V reference is 10 volts. Then the output of the digital counter is
3, no?
3. Like it is the binary equivalent I have to show for the digital counter, right?
Yeah,
0, 0, 1, 1, right, sir?
It will be 1, 1, 0, 0, etc.
Yes, but it is not equivalent to the binary equivalent of the input voltage given, right?
It is why?
V in star I am giving 5 volts.
Yeah, it is 25 volt, yes. So
Yes, sir. But the digital counter is not giving the digital format of the 5 volts, right?
see, 5 volt it will not represented as 101. Okay. That depends, right? If the maximum value is the digital counter, which is the ADC, the maximum value, as I told you, we have a ADC. There's a supply, V supply, right? If V supply is 5 volt, then and it's suppose a 3-bit ADC, then it should show value 111. When my input voltage is 5 volt. When my input voltage is 2.5 volt, it should give a value of 3 or 4. So it should give a value 100. This is how the ADC works. Okay. Now suppose the same ADC had 3 volt at the input. Okay, so for 2.5 it will show around like 110 perhaps. That is how it changes. That depends on the span of the ADC.
Okay. Here we are like, sir, in this case, the Slope ADC, the V supply is different from the V reference, right?
No, you assume the V reference is same as the V supply.
Okay, sir. Okay. Then it is clear.
Hmm.
Thank you.
Okay. Yeah, how we got it? No, NREF and all is done in the design stage when they're designing. Okay, when they're designing this, when the designers are designing the ADC, they have to decide NREF, T, etc. That they will design it. Okay, that you don't need to worry about it. But they will tell what clock frequency T you must apply, what clock you must signal you must give, etc. Then it will work properly. What range of clock signals are there for this dual slope ADC to work as it is designed to work. Okay, so we proceed. So there is a successive approximation register ADC. So this meeting will end in 5 minutes. So after that, again, I will again start the meeting, and then you can join in again. So SAR ADC is a successive approximation register ADC, and it is widely used because it is very simple and it is very intuitive to understand. So let us assume over here, assume a 3-bit ADC. Okay, for simplicity, assume a 3-bit ADC, and let us assume the range. Okay, the V supply. Let us assume the V supply of the ADC to be equal to 3 volt. Okay. Now the input signal to the ADC, let us assume it is 1.4 volt. Assume. Okay. So 1.4 volt is how much? It is 14 upon 1.4 volt divided by 3 is how much? Okay. So can you tell it in
0.46.
0.46? Can you tell it in the fraction format? In the form of fractions.
7/15.
Okay, this value is not good. Okay, let us leave that. Let us assume this example only. So
Sir, it has to be 3 by 2 to the power 3, right?
yeah, 3 by 2 to the power 3. Yes, it should be in the form of 8 should be the denominator. Then it will be easy to understand. Okay, just leave it for the time being. Let us assume this is V output by V reference. V reference is the supply. Okay, 3 volt. So, or just for simplicity, let us put V reference supply is 1 volt. Okay. And the signal which I apply, the input signal, assume it to be 0.4 volt. Okay, it is 0.4 volt. If it is 0.4 volt, it will be around this value. Okay, it would be around this range. It would be around here. Okay, this is 0.4. Okay, so this is my input signal. So what it will happen is, this is my input signal. Initially, all these bits, okay, D2, D1, D0, they all are 0, 0, 0. When I tell it now, you start sampling, what it will do, it will set D2 to 1. All these are 0, 0. So when this D2 is 1, there's a DAC. So the DAC will convert this 1. Since my Vref is 1 volt and this is 100, the V output which I will get will be 0.5 volt. Okay, so 0.4 volt, it will compare with 0.5 volt. So you can see the output of this comparator will be 0. So what will happen is D2 will be set to 0. So it will come like this. It will come like this. It will come over here. Then once it realizes that the output of this is 0, it will set D2 to 0 and the other bits are as it is. Then the next cycle, what it will do, it will make D1 to be 1 and D2 will remain the same, D0 will remain the same. So when this is 0, 1, 0, the output will be 0.25. Output will be 0.25. And here it remains as 0.4. So 0.4 is greater than 0.25. So the value will be 1. So what it will do is the D1, it will still remain as 1. So my D1 will remain as 1. So it will come and it will come like this over here. Then it will make this, it will make 0, this 0 and 1 remain the same. Then the 0 it will convert to 1. So the 1, 1, it comes out to be 3 by 8. That is 0.375. So this will be 0.375. So 0.375 will compare with 0.4, and still this is greater than that. So this will be 1. So my D0 also will be 1. So it will come over here. So what is happening is my digital output will come 0, 1, 1. This is how the successful approximation resistor ADC works. Any queries, doubts in this?
Won't the if MSB is set to reset, won't the next bit of the MSB will be setted?
So are there any doubts in this?
Sir, how?
Oh, yes, yes.
Sir, finally, this 0, 1, 1 is taken as 0.375, right, sir?
See, this is the what happens is
This year calculating from the resolution of ADC.
yeah. So when this 0, 1, 1 goes through the DAC, okay, will give 0.375 volt. So this is my 0.4 volt was my input to my ADC. Because it's a 3-bit ADC, it gets converted to 0, 1, 1. Then when it passes to DAC, the DAC will give output 0.375 volt. So there's an error. This is the error. This is known as my quantization error. So what would happen is, if my resolution of my ADC was more, instead of 3 bits, it was like 10 bits. Okay. If it was 10 bits, then my error would be reduced. Now, my error can be at a maximum value of my error would be this much, 1 by 8. Maximum value of my error would be 1 by 8. That would be 0.125 volt. Okay. But when this reduces, this is 1 by 2 raised to 3 because it's a 3-bit ADC. But if the resolution of the ADC is increased, say it is made by 1 by 2 raised to 10, then this will become approximately 1 millivolt. Okay. So that is why we prefer a higher resolution ADC. But if it is a higher resolution ADC, means each time, like it is happening one cycle for setting 1 bit, the next cycle. So suppose this 3-bit ADC is taking, let us say, 6 cycles. Okay, 6 cycles. Then my 8-bit ADC will take around 16 cycles. So if I increase the number of bits, my delay will increase. The time for conversion will increase. But if I increase the number of bits, then only my resolution is improving and my error is reducing. So all this is like a trade-off. So depending
Sir,
on our yes.
This quantization error which we are speaking is actually suppose we are converting from analog to digital. We are missing some because of the limitation of resolution of the ADC. We are missing some value of analog signal at the digital.
Yeah. Yes.
That is what we are calling it as quantization error.
Yeah.
But if we talk about DAC, DAC, how that quantization error could be understood, sir? If you talk about DAC,
no, see,
same thing at the analog, we will have some error.
No. What is the quantization error? It is. Let us go back over here. This is my ADC, right? Suppose I have given it here 3 volt, 1 volt, okay, or 0.4 volt I have given. 3-bit ADC, it gets converted into 0, 1, 1, and then it passes through my DAC. It comes out to be 0.375 volt. So 0.44 volt cannot be represented in my digital domain. In my digital domain, its equivalent is 0.375 volt. Okay, that is the error. That is a limitation of digital control. So to overcome this limitation, I have to increase the resolution.
Sir, here we are talking about analog to digital and then digital to analog.
Yeah, this quantization error is the error in the digital platform. The digital platform, it is represented as 0, 1, 1. All right, and that is used in my controller, etc. So all that error will get propagated in my controller, everything. That is the thing.
Then this quantization error now is 0.025. Is it, sir?
Yeah, 0.025. Yes. So that is the issue. Now, if you go over here to the ADC, this one, suppose it was 0 volt. Okay, it will show 0. Suppose it was 0.125 volt. It will show 0, 0, 1. Okay, the least significant bit is set. Suppose the value was less than this. Okay, suppose the value was 0.0625. It will still show me 0, 0, 0. Okay, so such a small value it is not able to detect. So the resolution is 0.125 volt is the resolution, and only values greater than 0.125 volt or changes greater than 0.125 volt, the ADC can detect those changes. Okay.
Resolution we can understood, sir. Yeah.
Okay. So now I'll proceed with the DAC. Okay, so when the DAC also has certain resolution, it has. The more number of bits it can take, the higher the more accurate and fine analog output it can give. Okay, there's update rate, delay also there, and power consumption also there in the DAC. So very common and used DAC is the R2R ladder. Okay, what happens is based on these bit position S0, S1, S2, etc., the output of it will change. So the output is given like this. Okay, the output is given by B0, B1, B2, Bn minus 1. So when S0 is 0, the S0 is connected to ground, then B0 is 0. If it is connected over here, then B0 is 1. So you can apply Thevenin's theorem as well as superposition theorem, and you will get this expression. And based on which bit is set, you will get the output voltage, and the output voltage is an analog signal.
Sir, while deriving this Vout equation,
Yeah.
We are assuming that all B0, B1 are connected to 1.
No, we are not assuming that. No, what you have to do is you have to just assume that B0. First, assume B0 is 1. Okay, you assume B0 is 1, and then you will see the output voltage in terms of that. Okay, output voltage is some value K1 into B0. Then what you do is set all the other bits to 0 and put only you set B0 to 1. Next, what you do, you set B1 is equal to 1, so it will be 0, 1, 0, 0, 0. So V output, you will get it to be some K2 into B1. So you use this method, and then since it's a linear network, you can add superposition theorem.
Superposition.
And the output voltage is the sum of all these voltages, and so you will get this expression. Okay. And by Thevenin's theorem also you can apply, it will simplify. 2R and 2R becomes R. Then when it's connected in series with a resistance R, it becomes 2R. Then it gets connected in parallel with a 2R. So it becomes R. This is the advantage of this circuit. So you can, in your free time, you can try to solve it, and you'll be able to go online also. There are resources to understand this. So main concept over here is we set the bits, and depending on the bits we set, the output current changes, and the output current is converted into a voltage by this resistor network. Okay, by this resistor. So this is for the DAC, and the delay of the DAC is quite small as the delay of the ADC, but nevertheless there will be some delay in the DAC. Okay, and this is where a DAC is used in our digital implementation. The I reference of N is converted into IRef, and that is compared with the inductor current using an analog comparator. An analog comparator is being used. And this is for my mixed signal peak current control. Okay. This is how we are using a DAC. So now we will go to study various current sensing circuits. So, okay, or is there any doubts over here? Okay, so now I will proceed to study various current sensing circuits, which are very important. So why do I do current sensing? Because if we see this thing over here, if I want to find this IL, okay, I will not just directly take IL, I can directly bring it over here to the comparator. I need to sense it. I need a circuit which will sense it. In MATLAB and all these simulations, MATLAB and all, we just directly take it using a go-to block, etc. But that is not how we do it in a practical sense. We need a circuit to sense my inductor current. And what we do is we convert the inductor current to a proportional voltage signal. Okay, and that voltage signal is being used. So we use it for closed loop feedback control. If you want to do peak current mode control, varying current mode control, etc., we require the sensing of the current. Then we also want to limit the current. Okay, we don't want the current to go very high. So to set a limit on the current, we use it. Because if the current becomes too high, it might damage the switch because the switch is not rated for such a high value of current, or the inductor could get saturated. And then once it is saturated, it is a problematic. Its inductance further reduces. So that is why we want to set a maximum limit that the current should not exceed that. Okay, and that is for safety of the circuit also. Protection circuit also, we need to sense the current signal. All right. For the startup arrangement, when we want to start the circuit, okay, the circuit, the output voltage is at 0 volt. Okay, then it has to go from 0, it has to reach its reference value. So in this portion, we need to know the current information. We have to limit the current. Okay, what would happen usually is we have a capacitor. VC of 0 is 0. So if large amount of current, and this is my resistor, so the current comes, it will directly flow through the capacitor. Capacitor will act as a short circuit. So we would want to limit the current in the startup time. Finally, what happens in steady state, this will be like a 5 volt or my reference value. But in the initial condition, when we turn on the circuit, this capacitor voltage is at 0 volt. Okay. Then what will happen? The large amount of current will flow. So we want to limit the current. So for that also in startup also we require current sensing. It is preferred. Then for current sharing multi-phase converters, multi-phase, there are different phases, and we want the current to be divided equally in each phase. Otherwise, there would be higher losses and efficiency would reduce, etc. And the advantages of multi-phase might be lost. So for that, we require very good accurate current sensing. And that is very critical for multi-phase applications.
Sir, multi-phase, you are talking about interleaved converters, no?
Yeah, interleaved converters, interleaved buck, interleaved post, etc.
So the current coming into the inductor will coming from the source will split into several inductors.
Yeah, yes, exactly. For those things. So we give a phase shift for currents through the inductors, etc., so that the input current ripple is reduced. So when the input current ripple is reduced, then the capacitor requirements at the input side and output side get further reduced. So that is an advantage of multi-phase converters, interleaved converters. Okay. So now we will see the various types of current sensing circuits. So first of all, here is my buck converter. Okay, I have input capacitor. This is my half bridge. Okay, this is my main switch Q, and this is my complementary switch Q bar. So this is a synchronous buck converter. This is my inductor. This is my capacitor, and I connect a shunt resistor RSH in series with my inductor. So the current is flowing through this. So the inductor current is flowing through this. When the inductor current flows to the shunt resistor, it will generate a voltage. Okay, it will generate a voltage over here, and I set this RI, etc. to be very high. Okay. Also, the input impedance of the op-amp is very high. So this current which will flow over here will be negligible. It will be approximately 0. Okay. So the sensed output will be minus of RF upon RI into R shunt into IL. Okay, this will be my sensed current. And this is a op-amp, and it is like a differential connection is there. So any doubts about this? So in this case, usually the inductor current will be like this, right? So suppose this is my inductor current, my sense current also will be somewhat similar. There may be it will be scaled by some value, but it will be a actual voltage signal. Okay, it will be V sense. This will be V sense. So in this case, I'm getting the information of the current when it is rising, and I'm getting the information of the current when it is falling as well. Complete information is available for me. Then there are certain things to look into is the VCC, VE, etc. This will be like say 5 volt. This will be like minus 5 volt. So we'd be required to generate these voltages, etc. And accordingly we will be able to get the output. So there are no further queries. I'll proceed, or you have any doubts in this?
Now this is IL reference, sir.
Which one?
This V sense is the IL reference.
No, this is not my IL reference. This V sense is over here. In this circuit, this is my V sense. Okay. My V sense is proportional to my inductor current. The V sense signal is proportional to my inductor current signal, and that I'm using it. Okay. Because the actual inductor current is not available with me. I don't know. That inductor current is flowing through my inductor. How will I know that? So for that, I have to convert it into some equivalent voltage proportional to my inductor current. I need to know those gains, etc., because it is like a feedback gain, all that. And that I will use in my circuit. So now I will proceed to another type of current sensing. What's the problem over here? This will create additional resistive losses. Okay, ohmic losses will come because it will be R shunt into IL square losses will come. So there is another method is there. That is, instead of what we do is we have the inductor. Inductor will always have a DCR. Okay, the DC value of the resistance of the inductor. So what is important is this RL upon L should be equal to 1 by RC. No, it will be L upon R. Sorry. L upon R will be equal to 1 by RC. So these time constants of this circuit should match. Okay, once the time constant of this path and this path match, then the voltage across the capacitor, this VCX, will be some gain into the current flowing through the inductor. Okay, but the important part which you have to take into account is these time constants should match. Time constant is L by R over here, and this is 1 by RC. And this way we minimize certain amount of losses, and this Rx value will be very high, so that the current which will flow through here is very negligible as compared to the current flowing through the actual inductor. And again, the same differential amplifier connection is there. And then this is my sense output voltage. So any queries about this? Okay. So now we'll consider high side current sensing. Like this was a very many of you guys have. Why we do high side current sensing for peak current mode control. So what I do is I place the sense resistance at the high side path. So this in this buck converter, it is the main switch. Okay, this is your active switch. So this is the inductor current is actually like this. Okay, like this. This is my inductor current. So the current which I sense, okay, this is my sense current, which flows to the resistance R sense, is this current. Okay, it is only this current. Only this current is flowing through my resistance. Only this part. Okay, so that is represented over here. And the peak, this is the peak value. Okay, so if you doing peak current mode control, this is my peak reference is there. When it touches that point, then my switch is, this switch is turned off and the current through it becomes 0. Okay. So any queries about this?
No, that's it.
Okay. So one important thing is the sensing. We use some sort of op-amp, all that, right? We are using an op-amp for that. So these op-amps will have a voltage, a common mode voltage, which is equal to the input voltage. Okay, it is equal to the input voltage. So those op-amps should be rated. They should be rated to be able to withstand such high voltages. So if you want an op-amp which is able to withstand such high voltages, it would be a costly op-amp, etc. So what we could do is, if instead we do low side current sensing. So my op-amp I place over here. Okay, I place the op-amp over here. So in this case, the common mode voltage of the op-amp is approximately 0 volt. Okay, this R sense usually is very small. Okay, so the voltage drop across this is almost 0. Okay, it is of some magnitude, but it's almost 0. It's close to 0. And because it is the sensing the current flowing through this low side switch, it will have this shape. And in this case, valley current mode control is used. Okay, we use valley current mode control over here. So when it reaches the minimum value, the valley reference, we turn on this switch. And so the inductor current which was flowing like this, no, the inductor current which was flowing like this will start flowing like this.
Sir?
Yeah.
This common mode voltage which you are talking, this decides the value, the voltage that we can give it to each, both the inverting and non-inverting of amplifier. Suppose VCM is equal to 4, then we can give a maximum. We can give 4 volts to both the input terminals of op amp.
Yeah.
And also if one terminal is higher, suppose it is 4.5 and 4, then we can say the common mode voltage is 4 and the difference voltage is 0.5.
No, it's not that. Common mode voltage, if you go through an op amp, this is my op amp, okay? Minus plus V minus V plus. So my common mode voltage is usually given by V minus plus V plus divided by 2. And my differential voltage is V plus minus V minus. So they will be rated that you can apply maximum of 5 volt or 4 volt, etc. to each of these terminals. Something like that will be there in the data sheet. But the main point for you to remember is, see, usually these voltages will be very, very small. Okay, they'll be very, very small because you would have heard about the concept of virtual ground. There's a concept of virtual ground in an op amp. So these two voltages are approximately at the same potential. So V minus and V plus will almost be approximately same. There will be a very small difference. That is what is getting amplified in the differential amplifier. But it will be a very, very small, negligible value. So the common mode voltage in a magnitude sense, it is approximately 4 volts, assume. Okay, you don't need to be worried of 4.001 volt or 3.99 volt. That is not the thing. It is approximately 4 volt, you assume, and you proceed. So the main part to realize is this input voltage could be 12 volts. The common mode voltage would be 12 volt if it was high side current sensing. But whereas for low side current sensing, the common mode voltage will be 0 volt. So this would be better. Like there would be op amp which could be rated for lower voltages. It can be used. But for this case, we need to select a higher end op amp which is able to withstand these voltages. So that you will have to take into account. So this is just one of the things you must consider. There's another consideration is the op amp has a gain bandwidth product. Okay, there's a gain bandwidth product. And if you will see this, I didn't tell over here, the gain, what I told, the gain of this op amp is RF upon RI. Okay, it is set by these resistors. And that is what says the gain. Then we require certain bandwidth of the current sensing. Okay, our op amp must be capable of supplying that range of bandwidth. So there is a unity gain bandwidth product, that is multiplication of gain into bandwidth, which is approximately constant for the particular op amp. So if I increase the gain, then the bandwidth which it is capable of providing will reduce. So usually they say the bandwidth of the sensing should be at least be 10 times of the switching frequency. It should at least be 10 times of the switching frequency. Why we say that is, suppose you see this is my inductor current. Okay, this is my inductor current. This is at a frequency FSW. Okay, FSW is the frequency of this inductor current. But it is not just this component. There are other, if you can take the Fourier series, there'll be other components. There'll be a DC component. There'll be the FSW component. There'll be a 3 into FSW component, 5 FSW component, etc. All these components will be there. So we want these components also to be shown in the sense signal. And for that reason, we require a high bandwidth. Okay, a bandwidth which is greater than 10 into switching FSW. If that is the case, that is the requirement. Any doubts in this?
Sir, if we if the gain bandwidth ratio, if we keep this bandwidth to be at least 10 times FSW, then this V sense at the output is closely representing IL.
Yeah. See, my IL.
Yeah, the waveform of V sense, which is the scaled version of IL, will be closer to IL.
See, V sense will not come to be a scaled version of IL. We take it, we assume, or we like approximate it to be a scaled version of IL. If it should be a scaled version of IL, let us say if it should be a scaled version of IL, it should contain all the harmonics of IL. See, IL is actually, if you take the Fourier series, it's a DC value plus the first harmonic, fundamental harmonic, plus 3 into FSW, plus 5 into FSW, plus 7 into FSW, plus 9 into FSW, plus so on. Okay. This is the usual way for the inductor current because it is symmetric and other stuff. So the even harmonics are not present. So the odd harmonics only are there, the even harmonics are not there. Okay, because of certain symmetry, etc. So now my sense signal, if my sense signal should be actual a sensed gain into IL, then it should have all these harmonic components and this DC component, everything it should have. Okay, and this will go on till infinity. This harmonics will be very high. But if you know this, as you increase the order of the harmonic, the component, like see, this may be 50%, this may be 40%, this may be 3%, this may be 2%, this may be 1%, etc. like that. As the order of the harmonics increases, the content of that harmonic will reduce. So if we just assume only this part, we just take only these components, it will fairly represent my actual inductor current. To a good degree, it will provide it. Okay. That is why we need the bandwidth of the sensing circuit, and in this case, the op-amp, to be should be at least greater than 10 into my switching frequency.
Sir, here in this case, we will always have even this. Actually, this is out of the scope of this question since you have told I'm asking. This FSW will also have even components also, no, sir, because it is not symmetrical to vertical axis. Okay.
No, to my knowledge, it will not have. Also, if you remember, the sir had shown the FFT also in the lecture 58, 59 somewhere in the oscilloscope. He has shown the FFT, and it is like this. If you remember, it will be like this. My DC, there's something, then it will reduce, then there's one thing, then it will further increase like that. So this is at 0, this is at 200 kilohertz, this is at 600, this is at 2, 3, this is at 1,000, like that. And then when sir decreased the input voltage, he reduced the input voltage. What happened was the duty ratio, which earlier was greater than the duty ratio, which was earlier less than 0.5, it became greater than 0.5. Okay, and what happened was subharmonics came into the picture. Subharmonics came. And what happened was at 100 there was a peak. At 300 also there was a peak. These components also got added because of that subharmonic instability. Okay, this my diagram is not clear, but that's what sir showed. So when it was operating as a normal pure inductor current, let me go here. When it was operating like this as an actual steady state periodic inductor current, it was having 200 kilohertz component and directly the third harmonic 600 kilohertz component. 600 and first. Okay. 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 That's the thing. Okay. So here we did low side current sensing where only this part, the falling part of the inductor current is there. Information is available because only that part of the current is flowing over here. In high side, only this rising value. When the switch is on, that component of current only is available. That current information is only available. But if we connect it in series with the inductor, then the complete inductor current information is available for us. Okay. So this is there. These analog devices, these documents are very useful. Okay, they provide good information, and I've read them. They're very useful. Now we will study. Now we just consider DCR current sensing as well as resistive current sensing. Now we will study how we can do current sensing using a transformer, current transformer. So what is the advantage of a current transformer is these are separated. This is my power circuit and this is my control circuit. Okay. So what is happening is we know IP into NP is equal to NS into IS. NS is the number of turns in the secondary, NP is the number of turns in the primary, and IP is the current flowing in the primary, IS is the current flowing in the secondary. And there are various commercial current transformers available. Usually, once I've seen, NP is 1 and NS will be very high in the order of 100, 50, etc. Okay, such that this IS current will be of a low magnitude. Okay, it will be of a low magnitude. Now, this input current IP is converted into a current signal IS, which is proportional to the input current. That has to be converted into a form of voltage. So for that, it flows to this resistor and it will generate an output voltage. So my V output will be R into IS. So when my current, this is a dot convention. So when the current is flowing in, the current flowing into the dot, the current should flow out of the dot. Okay. Now this, assume it be at this is my ground. This is my inductor and my capacitor and ground and resistor. Assume this is like low side current sensing, low side current sensing. So how will the current be? It will be like this. This will be a waveform. This is the peak value, this is the valley point, and this is the current which is flowing through the MOSFET, and this is the current which is flowing through my current transformer. So I would want this V output also to be of similar value, to be like this, and like this. Okay, proportional. We want it to be proportional. Now, when this current goes to 0, what will happen is we don't want the current to flow in the opposite direction. We don't want the current to flow in the opposite direction because then this value will become negative. This value will become negative. So that's why we place the diode to prevent the current from flowing in the opposite direction. Okay. Any queries regarding this? The meeting will end in 2 minutes. And then I'll again start this meeting. But any doubts over here? Banerjee, Dharmaraj? If there are no doubts, I'll proceed. Okay, why are we preventing negative cycle is? Okay, I have observed it being used for low side current sensing, so I was talking in the sense of that. So usually this is referred to the ground. Okay, this is referred to the ground, and this is my output voltage. Okay, this will be going to suppose my ADC, etc. So in usual practice, the ADC is single-ended. Okay, it is single-ended. So it will accept voltage at say approximately between 0 to 3.3 volt. It will not accept voltages which are negative. Okay, so to prevent it from going negative, that negative signal to come over here, that is why we have this. All right. we don't want it to become negative. So next we'll consider Hall current sensor. So suppose this is my current which is flowing through this conductor, and based on a Hall effect, it will generate some output voltage which is proportional to my current which is flowing. So this concept is used in Hall current sensors. So this is a Hall current sensor which is there. Okay. What it will do is, this is the current which will flow in and the current which is flowing out. Then it will generate this output voltage. This output voltage will generate, which is proportional to my current which is flowing in. Now, one advantage of this circuit is it can have high bandwidth. Okay, it has a high bandwidth and it is isolated. So isolation is very important in our circuits. What happens is the power signal should be isolated from my control signal. We want to decouple it, so the effect, like the problems or some noise from one part should not flow into the other part, etc. That is preferred. So when we have isolation, it doesn't affect. Okay, this power signal will not affect the control signal, etc. That is there. So the Hall current sensor is isolated current sensor. Okay, and here we usually give the supply. It's here around 3.3 volt. This is the biasing supply for this Hall current sensor. And this input is with respect to some other ground. This input current is flowing with respect to some other ground. So this supports, this IC, it supports bidirectional current. Okay, bidirectional current it can sense. So if the input current over here was 0, the input current here was 0, my V output would come out to be 1.65 volt. If my input current was, say, its maximum value minus IP max, then my V output will come out to be 0 volt. And if it was plus IP max, my V output would have come out to be 3.3 volt. Okay. So in this way,
sir, how the inductor, like you are saying it is about the sensing of the inductor current?
Yes.
If that is the case, how will we get the inductor current, sir, from our hardware setup?
Okay. So in this case, we will get a signal which is, let us see here. This is my inductor current signal, right? Suppose this is 0. This is my IL. Okay. My signal will come like this. Okay. This is okay, fine. But there will be some sort of offset, additional offset is there. Okay. That offset is like 1.65 volt. So my sent signal will be 1.65 plus K into IL. So when I want to use this signal for my operation, like for my for using it in a comparator, etc., I would need to have a circuit which will subtract. My V sensed must be subtracted by minus 1.65. Then only I will get it by K into IL. So there are certain circuits which can do that.
So then now this output of ADC requires a positive analog output.
So the advantage of this
Input.
is my ADC, if it is going to the ADC, if this V sense is going to the ADC, it will lie between 0 to 3.3 volt. Okay. I have an inductor current over here and I have a Hall current sensor over here. And that is generating my V sense. If my inductor current is around minus 40 ampere, it is generating 0. My inductor current is plus 40 ampere, it is generating 3.3. So even if the inductor current is negative, the ADC will only see a positive value. And then it will go into a digital number in the ADC. So in the previous cases, we We're not permitting the inductor current to become negative, etc. stuff. But here it can go negative and still it will be able to sense it. Any other doubt?
So then this that previous current transformer.
Yeah. What about this?
The previous method we saw, previous than this.
Previous to this. This one.
Yes. Here also we get bidirectional current sensing.
Yeah, bidirectional current sensing, but it is not isolated. See, this information, this is coming over here and just flowing over here, right? So it is not isolated. Isolation is what? This IL sense ground. This IL sense is a signal, okay? It is a signal that is with respect to this ground. Okay, this is the IL sense is with respect to this ground. And my signal also, which is flowing IL, is also with respect to this ground. But if you see a transformer, this is my V1, this is my V2. This is my ground 1, this is my ground 2. They are separated, they are isolated from each other. That is not there in this circuit.
There also in our Hall-Effler sensing also the current IL is the signal. It is the signal, right?
Yes, in the Hall current sensor.
The power.
Okay. So
the
here,
IC, yeah, here. This.
Yes. So here,
this power.
Tell, still complete. Sorry.
Can I tell?
Yeah, tell.
Sir, this power circuit is this 3.3 volt with respect to ground pin 9. Okay, this is different ground.
Yeah, this is a different ground.
Pin number 9 and 10 are different IC circuits.
Different ground. So this is my, suppose this is my buck converter. Okay, this is my buck converter. Buck converter's IL is flowing. Okay, that is with respect to some ground that is known as my power ground, assume. Okay, and this ground is my signal ground. So these two grounds are separate. These two grounds are separate. But in the previous cases, they were not separate. They were same. In the because what is happening is this is my buck converter. This is my high side switch, low side switch, my inductor, my capacitor, my resistor. This is my input voltage. And this is my power ground. Okay. And this is my inductor current. Yeah. So the inductor current is flowing in, and it is flowing in the power ground plot. But this is a different ground. This is my signal ground. So the effects and noise, etc. of this side will not come in this side. That is why we use isolation.
Sir, anyway, when we are giving back the gate signal to the MOSFET, up low, high side or low side MOSFET, again we will drive with respect to the power ground only. Yeah. Suppose we are driving the low side MOSFET. Yes.
You're correct. So in that case, we need an isolated gate driver. So in that case,
okay, that driver is a different circuit now. It has a different ground.
That will be a different driver. That would be like you see. This is a different page. Okay, assume over here. So I've not actually included the isolated gate driver. I was planning to, but I did not. But this is an isolated gate driver. Okay. This will be my V bias of the primary side, and this will be my V supply of my secondary side. Okay. This is with respect to power ground. This would be with respect to my signal ground. Okay. This is my PWM1. This is my PWM2. And this is my high side. It goes to my high side MOSFET, and this goes to my low side MOSFET. Okay. So in between this, there is isolation. There will be isolation. These grounds are not the same. So I will give them my microcontroller or my FPGA will give a PWM signal with respect to my signal ground. But when it passes through the gate driver and it is given to the MOSFET to turn it on, it will be with respect to my power ground.
Sir, this is for low side switch. Suppose if it is a high side switch, then this power ground won't be existing there.
Then we can use bootstrap arrangement is possible over that.
Okay. Okay. For low side, we can use isolated some optocoupler driver, and then at the top we can give bootstrap. Something like that.
Okay, that is there are various possibilities, but actually this would not, there would be some issue over here. This would only be for one low side. Okay, assume it is for low side. It cannot give for two things at a time. It can give for two things if we connect a bootstrap arrangement also. But it is usually not recommended to use bootstrap. There's one actually a very good document. I can attach that also to the video link, and you can see various types of isolated gate driver circuits. Okay, you could also use what is known as a optocoupler, and then you can use an actual normal plain gate driver, low side gate driver you can use, or you can use two isolated gate drivers. So these arrangements are there. Various different methods we can use for having isolation between our PWM signal and our gate signal. There are different methods are there. So when we go to the gate driver part, I will talk about this further. Okay. So this is for my Hall sensors, and then let us consider isolated current shunt. Okay, there are isolation amplifiers, etc. are there. This differential voltage over here is converted into another differential signal. Okay.
But does all these current measurements to sense the inductor current only?
No, it can sense the current flowing to the switch also, right? In low side current sensing, I am sensing the current flowing to the switch. I am sensing the current which is flowing to the switch. I am not sensing the inductor current here. This is my inductor current, and this is my current flowing through my switch, right? That way.
So this is the low side current sensing that we are seeing, the diagram we are showing here.
Okay, over here.
Yeah.
It can be for low side current, it can be for high side current, say anything. They're just showing an equivalent circuit. It is not required that there should be ground and all that stuff. Okay. They're just showing it. Just assume, forget this. Just there's a current which is flowing through a resistor, and the voltage across that we are sending it to an isolation amplifier. Okay. So the isolation amplifier has a differential input, and it will create a differential output proportional with some gain. Okay, gain may be around 8, 8.2, etc. That gain. I'll show one circuit, actual circuit. So this is my isolation amplifier. There are various other biasing capacitors, decoupling capacitors, all that. You can ignore that. what you must remember is this is my power ground. Okay, this ground 2 is my power ground, and this is my this is not my power. This is my signal ground, and my ground 1 is my power ground. And there is a current which is flowing, and that is going to my sense resistor. So that voltage which is produced across the sense resistor comes over here and over here via an RC filter, etc. So this is the equivalent voltage which comes over here. Okay, that passes through my isolation op amp. This isolated ISO op amp, and it will generate a differential voltage over here, which is proportional to the difference of this with some gain. Gain of this, I think, is 8. So if over here V input plus minus V input minus was around, say, 150 millivolt. So V output plus minus V output minus would be like 150 into 8 will be 1.2 volt. Okay, around 1.2 volt. So this would be the voltage 1.2 volt, and that is passed, and this is a differential amplifier. What does the differential amplifier does? This is a differential signal supplied here, and it generates a single-ended signal. It generates a single-ended signal with respect to my ground, and then the signal can go to my ADC, or it can either go to my comparator, etc.
Sir, it would be better if you demonstrate the difference between the isolation and the non-isolated. Like if the grounds are different, what benefit we are getting and what are the drawbacks if they have same grounds?
Okay. No. See, there'll be certain noise. There'll be certain noise, if you see. There'll be the noise from the sense resistor, and other factors also are there. And they can be influenced. There's a problem of ground bounds. Ground bounds are the influences, because the ground of this and the ground of that, and there's some sort of track length in between. Grounds may not be at the same potential, etc. So those effects, to counteract those effects, if the grounds are isolated, then those effects will not come into the picture. Then there's something known as common mode noise. So that common mode noise, because we are using the differential sensing, we are reducing that common mode noise. And that common mode noise of a power ground is not transferred to the signal ground. That is the advantage here. The common mode noise which is there in the power ground is not transferred to the signal ground because there's an isolation. That prevents the common mode noise from passing from the power ground to the signal ground. So there are various advantages of it.
Sir, is there any document where we can refer to this like isolation and non-isolated noise? And
there's a document of that isolated gate driver, so that I will attach in the YouTube channel. Okay.
Okay.
Sir, here that ADC output, it won't be single-ended, right? This V out. V out that we are getting. Sorry,
yes,
not
yes,
ADC output. This V out.
It is single.
Because it has
it is with respect to my ground too.
Yeah, but here are minus 15 volts also.
See, single-ended means what? It is with respect to something. Okay, it could be with respect to ground, or it could be with respect to something else. See, this single-ended signal V output can be with respect to my ground 0 volt, or it could be with respect to 2.5 volt, etc. Something else. That is not the issue. But it is a single-ended signal. Usually, if a differential signal will have this, will have some value, and it would be superimposed on that. It would be in opposite phase. Then when it passes through my differential op amp, it generates this signal, okay, a single signal. That is why it is single-ended.
Could you please repeat it once?
Yeah. Actually, this polarity is wrong. This is plus, this is minus. Okay, this is my V input minus, this is my V input plus. Sorry, this is minus, this is plus. When they pass my differential op-amp, it will generate an output signal, which is only one signal, which is equal to the difference of these signals. So my input signal was two signals, okay, which had a, this is their common mode value. This is their common mode value, and this was their part which is oscillating around that common value. And that, what happens is that the common mode signal is not there anymore, okay, because plus or minus the common mode value gets subtracted off, gets eliminated, and only the differential component, it gets amplified and is available over here. Okay, that is why it is a single-ended signal.
Single-ended in the sense only one output.
Yes, only
there.
only one signal is there. Yes. Yeah.
Yes, if the output is like, I saw some figures where the output is shown with respect to like plus VSAT and minus VSAT.
Plus VSAT and minus VSAT.
Yes.
You are talking of, see, don't, one thing I'm thinking this is your confusion. I may be wrong, but what I think is you guys are assuming that V output should only be positive. Okay. V output can also be negative because the op-amp has minus 15 volt and plus 15 volt. So my output can lie between minus 15 to plus 15. Okay. See, the main point which I want to tell you is this signal, okay, this is a voltage signal. This is a Vx and Vy are there. Vx and Vy, the difference over here. Again, Vx minus Vy is the input to my differential op-amp, to my isolated op-amp, and then that generates another differential signal, okay? Suppose this is Va and Vb. So my Va will be V common mode plus Vdm plus. My Vb will be V common mode minus Vdm minus. Then when it passes through my op-amp, my V output will be some gain G into Vdm plus minus of minus Vdm minus will be plus Vdm minus. So it gets converted into, so over here, the information of this inductor current is in two signals, Vx and Vy. Over here, it is also still in two signals, Va and Vb. But finally, the information of the inductor current is in just one signal, V output. So it is single-ended.
Sir, won't there be double-ended?
Double-ended? No, we don't want those double-ended signals. We want it to be single-ended because then it will go only to an. It is preferred because then we have to use only one input pin. If it is double-ended, we require two pins. That is a problem.
These two pins will be like for op-amp only one output will be there. If we are interested for a double-ended, like V out is one thing and the other comes from where?
It cannot be done. With this configuration, it cannot be done because this is a differential op-amp, differential amplifier, which is used specifically to convert a double differential signal to a single-ended signal. Okay.
Okay.
So, sir, again with this equation, V out equal to G into Vdm plus Vdm minus. Again, now it becomes positive always.
No, it may not be the case. No, if Vdm plus is negative, then what will happen? Then it could become negative, right? mean to say
VDM plus is negative, then it becomes 0.
no. Just see, VDM plus and VDM minus, they need not be equal. Okay, they need not be equal. Just representing it in some sort of format like that over here. Okay, so just consider. Let me think. It can go negative. The output can go negative because this voltage VDM can be negative. This VDM minus also can be negative. So it could go negative, right? There's no constraint on that.
Because we are saying it is both are riding on common mode. The common mode it becomes 0. So for the voltage to amplify at the output, these two should be of opposite sign, so that if you subtract it becomes positive.
That's not always the case. No, see now over here, you see over here, this is my 0. This is my 0 volt. So my output is becoming negative as well, right? It is going negative. It is going negative, right?
Exactly.
Okay, so we'll proceed further. So this is another way of isolated current sensing. Now we will go for ADC and DAC. They have drivers. Okay, we'll go quickly through this. So this is my output voltage. We have a ADC driver, and then that goes to the ADC, and then we get a signal. So what they say is the ADC driver converts a single-ended or differential-ended signal to a differential amplifier. When we see over here, this is my ADC driver. Okay, this is my single-ended signal. Okay, my single-ended signal is with respect to my ground. Okay, with respect to my ground, that this ADC driver converts it into a differential signal. Okay, differential signal means there will be a common mode value upon which it will add these differential components, and that will go to my ADC, and from the ADC it will go as a digital output. Okay, the ADC will give a digital output. So the goal of this ADC driver is it will either convert the single-ended signal to differential signal, or the differential signal itself it will amplify it further and it will provide to the ADC. Okay, because the ADC works better when this signal is a differential signal, which they have shown over here. So in this board, they have used a differential signal. The input signal is single-ended. Okay, the input signal is single-ended. Via a ADC driver, they're converting it into a differential signal, which is going to the ADC, and the ADC is converting it into a digital output. Okay. So next. So this is the ADC which they're using, and they're using a 10-bit ADC is being used. So the ADC, if you will remember, there'll be a clock to my ADC. So this clock will tell the ADC when it should start converting if you take the sampler and you should start converting it into a digital value. So there's a 5-cycle delay. Okay, there's a 5-cycle delay, and this is a pipeline ADC. So suppose this is my analog signal over here. Okay, this is my analog signal over here. That is available after these 5 cycles in the digital format. It is available over here. So although I'm taking the sample over here, it is available over here. And the signal n-1 which is available here has been sampled prior to that. Okay, so there's a 5-cycle delay after which I will get my digital data. So this is a problem with ADC. There is a delay. So in this board, in the board which the sir has used for the hardware demonstration, they have used the pipeline ADC, which has a delay of 5 cycles. So any doubts in this?
Sir, is this delay that can't be avoided, or can we configure according to our requirement?
This delay can't be avoided. It is inbuilt.
Okay, it is fixed.
It is
for an ADC.
For this ADC. But if we decrease the time period, then the delay will reduce, right? It just cycles.
How so?
This is a time period T, right? Suppose this T is 1 microsecond. So my delay is 5 microseconds, right? But if I make T to be equal to 0.1 microsecond, then my delay will be, sorry, my handwriting, it will be 0.5 microsecond, right? This way I can reduce my delay.
Sir, this timing diagram.
Mm-hmm.
Sir, this AD9215. Mm-hmm. This is the ADC, right, sir?
Yeah, this is ADC, right? Yes.
And then this delay is both consisting of both the gate driver delay as well as ADC delay.
No. Why? Both of the ADC driver delay, not gate driver delay. ADC driver delay.
ADC driver. ADC.
Okay. Yes. No, in this timing diagram they've just shown the ADC's delay. Okay. The ADC driver delay they have not shown over here. But that would be
Sir, you are saying that this delay is dependent on the number of cycles itself, right?
Yes.
Okay. If we are able to decrease the time period of that cycles, then the delay time will be reduced.
Yes, exactly.
Okay, sir. Thank you.
Okay. So these are certain specifications of how much. See, we just cannot keep reducing this T, okay? This T, which I told make it 0.1 microsecond, you cannot reduce it below. You cannot assume to make it 1 nanosecond, etc. Make it and it would not be able to convert it. Okay, there is a certain limit. So you have to take that into account, and that you will be able to find from the data sheet. Okay. Then there is a DAC. Okay, they have used a 12-bit DAC. Okay, it is preferred.
Sir, that.
Yes.
Sir, the minimum T that we can use depends on the sampling rate, is it?
Yeah. The sampling rate we cannot make it very high. Yes. So F sample is actually equal to 1 upon T. Okay. So we cannot make the sampling rate arbitrarily large just on our wish. It is constrained by the ADC specifications.
Then, sir, the minimum T that we can give decided by the sampling rate only, is it?
Yeah, they're the same. Because they're related, right? They're inversely proportional. No? F sampling is 1 upon T.
So this 80 MSPS decides the T here, minimum T. In this specification.
In this specification, actually, this is bit. I'm not exactly sure about the specifications, what they're actually referring to. Okay. Because it is 80 MSPS and this is 9.5. That is creating an issue. So if suppose the minimum clock period is 9.5. Okay. 9.5 nanosecond. What is the inverse of 1 upon 9.5 nanosecond? It would be 1000 upon 9.5. Approximately 100. It's 100 megasamples per second. But here it is showing 80 megasamples. This one I don't know. Okay. Yeah, this we can see later. See over here, they have the delay. 5 cycles is the delay. Okay, this is the delay pipeline delay shown. So it's for 5 cycles. And this is a wake up time. So it will take approximately 7 milliseconds for the ADC to power on everything. Okay, so those things also you have to consider when you're doing your hardware. All that. Then there's a 12-bit DAC they've used. Also, what the problem with the DAC is, it will generate very low current. Okay, 2 milliampere, 20 milliampere. So when we are doing this over here, we are seeing that output DAC is directly given over here. Okay, but it might not be feasible. Okay, the signal may not have enough power. So what we do is we give a DAC driver. So the digital input gets converted into a differential output from the DAC. So this is a digital value. It gets converted into an analog value, but a differential analog value. And that using a DAC driver, we get a single-ended analog output. Okay, so the differential output of the DAC gets converted into a single-ended analog output. So, and one of the reasons is because of the capability of this DAC. It has a very low current capability. So we use a DAC driver to increase the power and etc. So now we will consider gate drivers. So this is a simple half bridge gate driver. So what is a half bridge? A half bridge is one switch over here and another switch over here. Okay. This is my V power, V rail, and this is my half bridge. This is S1, S2. So this is my high side switch, this is my low side switch. So what happens is, this is a half bridge gate driver. This is connected to my high side switch, and this is connected to my low side switch. So we'll see this circuit. Okay. So this is MOSFET, high side MOSFET. This is my low side MOSFET. Now, this is from my controller. Okay. This is from my controller. This is my PWM. PWM for my low side. PWM for my high side. Okay. And this is my supply, biasing supply for my gate driver. This is a simple half bridge gate driver. This is not isolated. Okay, so this VCC is with respect to this ground, and this ground is same as my power ground. Okay, this ground is same as my power ground. In this case, what is happening is this. You should remember that VCC, say approximately, will be equal to 12 volt or something. Okay, and the threshold of the MOSFET will be around 5 volt something. So it should be greater. This VCC should be greater than the threshold of the MOSFET to turn on the MOSFET. So what is happening over here is, suppose we give the low side switch is high. This PWM low, we give it to be high. PWM low is high, then PWM high will be low. Because these switches are complementary. So when this is on, this has to be off. And vice versa. Because if both switches are on, then the output voltage will directly flow through this these two MOSFETs, and then lots of current will flow and it will damage. Okay, it's like a short circuit. So there will be complementary. There will also be a dead time will be available, etc. Those are complex things. So now we will just start a simple thing. I want to turn on this MOSFET. So what do I have to do? I have to apply a voltage of between, this is the gate of the MOSFET, this is the source of the MOSFET. So I must apply a voltage at VGS which is greater than or equal to my threshold voltage to turn on my MOSFET. So this shunt, you ignore it. Okay, this is not that. It's directly connected to my ground. This is my ground. So I have to assume the ground is at 0 volt. So at the gate, I have to apply a voltage of around, 12 volt. So what happens is, when I give a high, when I give to my low side input, I give a high value, this value. Then what happens over here?
Sir, where actually you are giving high, sir? Like one thing is clear that
input of QL. Sir, here we are written at the bottom MOSFET 12 volts. No, it has to be 5.
Where?
Or 12.
Sir,
So
please
at
start the
the
explanation from the beginning for this gate driver, please.
Okay, yes. So this is my gate driver, okay? And this is my input to my gate driver. So if you remember, so I had shown that the gate driver is like actually two back-to-back buffers. Okay, it is like two back-to-back buffers. So I give here 1, it becomes 0, and it becomes 1. Okay. So what? Okay, this is not the correct explanation for this part. Okay, let us see. I give a signal over here. This Ln is for my low side MOSFET. Okay, this Ln is for my low side MOSFET. This Hn is for my high side MOSFET. So Hn is the PWM signal for my high side MOSFET, and Ln is my PWM signal for my low side MOSFET. So this PWM signal will be of around 3.3 volt or 2 volt, etc. something. But to turn on the MOSFET, I need a high voltage, okay, which is the voltage across the gate to source of the MOSFET should be greater than the threshold voltage of the MOSFET. So the higher the VGS, the faster the MOSFET will turn on. So assume I put VCC, I connect VCC to 12 volt. Okay, the supply, this VCC supply, bias supply, I assume it to be 12 volt. Then what happens is when this low side thing PWM is, this is 1, okay, that is it is logic level high. That would mean that I need to turn on this MOSFET, and to turn on this MOSFET, what I have to do is this switch, okay, this MOSFET, internal MOSFET will turn on, and from the ground, from VCC 12 volt, it will go over here, and it will flow over here. It will flow through the ground, and from the ground it will come off here. Okay, so this is how I effectively, what I'm doing is I'm applying 12 volt. I'm applying 12 volt across my gate to source of my low side MOSFET, and I am turning it on.
Sir, you have given VCC 12 volts at the top corner,
Yes.
like top left.
Yes.
How we are getting that 12 volts
They're
in the
internally connected.
QLs?
Inside the IC, they're internally connected. This is connected to VCC internally in the IC.
there is also another VCC here, must with
Yeah,
RP VCC.
Yeah, this also is there. This also is another VCC, but it's the same. Both these VCCs are the same, actually. Okay.
Okay, this VCC is getting added to this 3.3 volts. How we are getting it? It is getting added.
No, this is just logic. This is logic. If the logic over here is 1, that would mean this MOSFET has to turn on, and when this MOSFET turns on, it is connected to 12 volt. Okay, so 12 volt comes over here, is applied over here, and this is
Okay,
connected
we are
to my
actually
ground.
VGS is 12 volts, right?
Yes, VGS is 12 volt.
Okay, okay.
Then when this is turned off, okay, when the logic over here becomes 0, then this MOSFET turns on. So this entire thing will discharge like this. Okay, and it is, so effectively we are applying 0 volt to the MOSFET, and the MOSFET switches off.
Okay, sir.
So this is for the low side MOSFET. It is simple. Okay, I applied 12 volt, which should be with respect to my power ground. But if I want to turn on this MOSFET, I need to apply 12 volt with respect to this node. Okay, my switching node. I need to apply 12 volt with respect to this node. And how will we do that? So to do that, what they do is, there's a bootstrap capacitor arrangement. So when this MOSFET is on, okay, when this MOSFET is on, this driver voltage, this 12 volt, it flows to the diode and the capacitor, and it charges it to 12 volt. So when this MOSFET is on, the voltage over here is approximately 0 volt. Okay, it's approximately 0 volt. Why? Because the MOSFET is on, it is like a short circuit, it is acting, so it is connected to ground almost. So my boot capacitor gets charged through the V drive, that is 12 volt. Then when this MOSFET is turned off, okay, then this is no longer at 0 volt. It is some value, okay, some value VSW, assume it is VSW. Then if I want to turn on this MOSFET, I need to apply over here a voltage which is VSW plus 12. So that my VGS, which is equal to my gate voltage minus my source voltage, gate voltage should be VSW plus 12, and my source voltage is VSW. So my effectively my gate source voltage will be 12 volt. So to do that, what I have to do is I have to generate over here a voltage which is VSW plus 12. But that is not possible because VSW can change accordingly, it can vary, etc. So what we do is a bootstrap capacitor arrangement. So my bootstrap capacitor gets charged to 12 volt. Okay, once it is charged to 12 volt, then when this MOSFET is turned off and this VSW comes some particular value, and then when we want to turn on this MOSFET, what it will do is, this is already charged, the voltage over difference over here is 12 volt. Voltage across the capacitor is fixed to 12 volt. It can be either with respect to the ground 0 volt, or it could be either with respect to VSW. That does not matter because the capacitor is just holding some charge and the effective voltage across the capacitor is 12 volt. So once this is turned off, the voltage over here comes to some other value. The voltage at this node comes out to be VSW plus 12. Okay, the voltage over here comes out to be, I'm sorry, let me just miss. Those are useless things. So,
sir, you are saying this VSW plus 12 minus VSW should be greater than VGS threshold.
V threshold, yes. Yes. So over here, it comes out to be VSW plus 12. Okay, VSW plus 12. Then when I want to turn on this MOSFET, what I will do, I'll give PWM high. When I give PWM high, this voltage over here gets connected over here. Okay, and approximately I am applying a difference of 12 volt here. If this is a very confusing thing, you want me to repeat, I'll repeat it again.
Sir, please repeat it one.
Okay.
Sir,
so,
I'm clear up to the point that the capacitor is charged to plus 12 volts. It is clear.
mm-hmm.
Then
Sir, here you are saying
saying
VGS threshold is 12 volts, right?
Yeah, VGS threshold is 12 volt, yes. Okay, see, this VG which I'm saying is with respect to this ground. This VS which I'm saying is with respect to this ground. All right. So what happens is,
sir, please repeat this.
yes.
Sir, these references are with respect
Yes.
to which? Please repeat.
Everything I refer with respect to this ground. Okay, my VDRV, just 12 volt, is with respect to this ground. So what happens when I give logic 1 over here, then this part gets connected over here. Okay, effectively what is happening is I'm connecting 12 volt to my VGS of the MOSFET, and it is turning on. Okay, this is simple because my V drive is also referred to the ground. But over here, if I just connect VDRV over here, directly over here, what if this bootstrap capacitor, all this arrangement was not there? At this place, I will be getting 12 volt with respect to this power ground. But my VSW assume it is 30 volt. VSW assume it is 30 volt. So what I would require at this part to actually be 30 plus 12 volt. Okay, I require it to be 30 plus 12 volt, but that is not happening. So what we do is we use a bootstrap capacitor. So the bootstrap capacitor gets charged to 12 volt, okay, across it, and then what do? We apply the bootstrap capacitor from via this terminal, and the effective voltage across the bootstrap capacitor is applied across the gate source voltage of the MOSFET, and the MOSFET turns on.
Sir, the thing I'm getting confused is, sir, this VSW and this 12 volts are different, you're saying?
Yeah, they're different.
Sir, if it is VSW, then the capacitor will be charged to VSW, right?
No, this is my capacitor. The voltage at the bottom of the capacitor is VSW, and the voltage across the capacitor is 12 volt. And the voltage at the top of the capacitor
Sir, at
is
that
VSW
time, the lower
plus
switch
12.
is off.
Yes, at that time low switch is off, yes.
Sir, plus 12 volts we are getting from the V driver, we are getting plus 12 volts.
Yes.
But how we are getting VSW, sir?
VSWs come from the external circuit. VSW is not under our control. Because VSW is not under our control, we need an arrangement which will generate a voltage of 12 volt across the VGS. So irrespective of the voltage VSW, I want to guarantee that my voltage across my gate source capacitance should be greater than my threshold voltage. So I want it to be around 12 volt. Okay.
Sir, if that is the case, if VSW is not in our control, then how we are getting VSW plus 12, sir?
Yes, because I have charged the capacitor to 12 volt. Okay. The
Yes, that's fine.
capacitor is 12 volt. And at the bottom, see, this VSW can change. VSW can become 0, it can become 5, it can become 10. That is fine. But the voltage across the capacitor, I fixed it to be 12 volt. So over here, I will get 0 plus 12 or 5 plus 12 or 10 plus 12. That is fine. What I want is the difference. Difference between these 2 points should at least be 12 volt. Because that is only the difference, that voltage difference is only being applied to my gate source of my MOSFET. And that only will decide if the MOSFET will turn on or it will not turn on.
So here this controller has all the op-amps and every logic we have. It's op-amp and all the latch circuit, everything will be inside this controller, right?
No, this is just a simplified thing. Yeah. You mean that the PI controller,
Feedback.
auto stuff, feedback things?
Yes.
Yeah, that is all there. That is not shown because just for your basic understanding how to turn on, off. Is there. Okay. So Bootstrap half-bridge gate driver we have used in the training kit. Now the sensing circuits is this. Okay, this is for the current sensing. This is the one where the shunt resistors and the voltage across this is being measured. This RF1 and RF2 will be very high. Okay, Benergy, these will be very high. So effectively, no, we want to minimize the current which is flowing. The current flowing over here is minimum. Then this voltage V shunt will directly come over here. Okay, this will be V shunt. And then through the differential amplifier arrangement, we get it of this format. So this is my V
Sir, I have one doubt. Sir,
Yes.
if RF1 is very high, then we can neglect the R1 also, right? Then V plus
No,
minus V minus.
You cannot, because what is happening is RF1 and RF2 is very high. V shunt is coming, right? V shunt is coming. See, it is not that there's no current flowing. There's a negligible amount of current which is flowing. Into the op-amp also, very negligible amount of current will flow. That is one of the advantages of the op-amp. It has very high input impedance. Okay. So the currents will be very low. But the effect of this is negligible.
Okay.
Okay. This is a very important thing. It offers very high bandwidth. Then voltage sensing also we are using a differential amplifier. So if you want to derive these equations, we'll have to use this is what for that op-amp, you'll have to I don't know what those equations are called, but what you have to do, you have to neglect the capacitors. Okay, you have to neglect the capacitors and assume this current is flowing like this, one current is flowing like this. Okay, this
DC analysis.
DC analysis. Okay, DC analysis. You ignore the capacitor. Okay, and then you will get this.
Yeah.
This capacitor is just for as a filter to filter out the high frequency noise. And this is a very simple. This is actually just a differential amplifier. This is a differential amplifier. Then, okay. Now we just see certain board schematics are there. So this is the hardware. This is the test kit which is there. Okay. So So this is the hardware. So this is the buck or boost converter, both. It can be configured as a buck converter or as a boost converter. So this is the high voltage side, this is the low voltage side. And from here the signals are going, and this is the ADC, the DAC, etc. So this is the hardware prototype. Okay. These are the capacitors, input capacitor, output capacitor, and this is some signal for seeing the output voltage. This is a connector connecting the power stage to the signal conditioning stage. This is my DAC, this is my ADC, and for then these are some switches which are there, which are present for giving the load transient and other stuff. Okay, so this
output
is the
voltage.
yes.
Sir, here we are sensing this output voltage using this BNC connector, sir. Here, some gold color.
Yeah, this one.
Okay.
So I think there was some provision was not proper, connections were not available, so they used these wires after that. Okay, but this is a BNC connector is used. So this is a low voltage side. So when we configure it in a buck, see, this is a switch. We'll make it either buck converter or a boost converter. Okay, so now it is configured as a buck converter. So this is high voltage side is my input, low voltage side is my output. Okay. So now we will see this is the power stage schematic. So this is the V input plus. So these are capacitors. 1210 is 1210 SMD package. Okay, 0805 is the smaller capacitor package, and they connect in parallel so that you reduce the ESR. Then there's the Bootstrap gate driver, which we talked about, and there's the half bridge. This is the high side switch, there's the low side switch, and then over here from this switch node point, there's these terminals, they are open. So for that we have this. Okay, this wire is there. Why do we have this wire? Is this thing is because we connect a current probe across this. All right, so that way we can see what is the current flowing through the converter in the oscilloscope. We can see the actual current flowing. Those current probes are very, very costly. Okay, then after this power stage schematic, after this wire, then you have the inductor, and then you have the sensing resistor over here, and then after that this is the output capacitor. Again, they are connected in parallel to increase the capacitance and reduce the ESR. All right, then the current sensing circuit is shown over here. This is again the differential current sensing, and to configure it as a boost or buck, the different arrangements are provided, but that is not currently required for you. All these are not required for you to know or to understand. We're just showing it. So what they do when they prepare the board, they first make this sort of schematic. After they make the schematic, they will add the footprints of the capacitors, the sizes of the capacitors, the inductors, the resistors, etc. And then they will do the layout of it. So you guys would be knowing, but I'm just saying. Okay. So there's a current sensing circuit. Then for a load, okay, we want to give a load step up or step down. For that, let me check that. So this is my output voltage. Okay, my output current is given by output voltage divided by the load. Okay. So suppose my load current was 20 ampere. Now I want to make it 30 ampere. So what I have to do, I have to reduce this RL. So if I have to reduce the RL, I have to connect RL parallel some R1. Okay. So that is what happens here. There's a fixed resistance RL over here, and then there's a MOSFET over here, and then there's a resistors. So the circuit is like this. This is my RL, this is my R1. So when this is 1, then that means the effective resistance is R1 parallel RL. And when this signal is 0, my effective resistance is just RL, which is my fixed resistance. In this way, I will give a load transient. Okay. So this is possible. And then this is a voltage sensing circuit. Again, the same differential amplifier is used. And
Sir?
yes.
Sir, in the last case, here we are using that switch to give the load transitions in our PCB.
Yeah.
We are essentially at that case we are essentially firing this MOSFET.
Yes, exactly.
Okay.
Yeah.
Sir, similarly in the current measurement in the previous slide, the PCB, before the red color wire which we use.
Yes.
Yeah, this one, sir, to measure this current, if you want to see this in the DSO, we want to use that differential probe measurement. Which probe you have to use here, sir? You said it is costly.
You will see differential probe will measure the voltage, differential voltage, right? Current probe does that. It will.
No, you said it is costly.
Yeah. They are costly. It's just you need the funds to get it. Yeah. The different. The current probe is like it is wrapped around that. Okay. It will be wound around it.
Like a clamp meter, sir.
Yeah, it is like
clamp meter.
Clamp meter, I don't know, but it will be like wound around this. Okay. If you
sir, no, sir. What I'm asking is
yes.
whether something like clamp meter can be measured and seen that can be displayed in DSO. Something of that provision is available.
I actually don't know what's a clamp meter, so I'm not able to answer it.
Sir, it is actually like a tongs. In kitchen we use tongs like that.
Something will be wrapped around that wire.
Yes. Something which is wrapped around it. Yeah. The same thing. Yeah. So actually, what happens is this is my inductor, okay, and this is my switch, all that. So I cannot. This is all inside the PCB, so I cannot put something wire wrapped. So what we do is we give it as external provision of a wire. Okay. So I wrap around this. Okay. That's how it is done.
Okay, sir, you can proceed.
Yes. These are for the voltage sensing, current sensing. Then there is something of how we load the code into FPGA. Okay, so over here, if you will see, this is a good one. This black thing, this one, this is my current sensor, the current probe. Okay.
Which one, sir?
This black one, which I have put a circle around.
Sir, there is nothing visible here.
Oh, it's not visible. Now, is it visible?
Oh, yes, it's visible.
Yeah.
Now it is up.
Yeah, so that is put around across it. Okay. So what we do is we have to first identify what sort of architecture, what sort of control we are using. They will write a Verilog code. Then they will generate a bin file, and then we will load the file to FPGA. So this is the oscilloscope, which is showing the inductor current and the output voltage, right? And this is the power supply which is there, and this is the board which is there. Now,
the slide.
Yes.
Now it is up. Yes.
Okay. So now this ISC designer software is there. You can install it, and then you will create a new project, and then you will write the code over here. Okay. Then if you want to add a new module, you will add a new source and you will add a new module. Also, there's a certain file known as a UCF file. What is the UCF file? It contains that which pin of my FPGA gets mapped onto which terminal of the FPGA. So for that, we have something known as a UCF file is required, and that you can get it online also for whichever particular FPGA you're going to use. Okay. Then this is the place where I write the code for my module. And what I will do is I will generate the file. Okay. Also, there are certain properties of the module which you can get. So 1 minute. Then we can run the file. Alright. And for running the file, we must also select the .bin file. Once we select the .bin file and we select it, now we want to see at which port the FPGA is actually connected. Okay, which serial port FPGA is connected. So initially the FPGA has not been connected. Once it gets connected, it will show this COM file. Okay, just we have to go to the device manager in our desktop and we have to find it. And this says now the USB serial device is connected to COM file. So when we are selecting it, which port you want it to communicate with, how will you communicate from the computer or laptop to my FPGA? I'm going to use which terminal, which communication port, so that for this particular computer, COM5 was used. That for your particular computer, you'll have to decide on your own. Okay, you'll have to go to device manager and see, which is for the USB communication port. Then you have to configure it for COM5, and then you have to include the bin file, and then you have to program it. And then when you program it, it will dump the Verilog code into the FPGA. So it takes some time to actually dump the code into the FPGA. It will, it is not like instantaneous. It takes some time. So once it is done, and then it will start running. Okay, the code is ready for it to run. So main part is you have to write the FPGA code. Okay, you write the FPGA code in those modules. Okay, and you have to also have the UCF file particularly for the FPGA. And then after you write this module, then you have to generate the bin file, and then you have to find out which port, okay, you're going to use to communicate between your laptop to your FPGA. Okay, once you identify that, then you can use that to dump the code. Dump the code is like you're burning the code which you have written into the FPGA, and once it is written inside the FPGA, that code is there in the FPGA. Then you don't need to use it. That means then you don't need to again keep it connected to your computer. You just need to power on the FPGA, and that code will be running internally in the FPGA. Okay. So with that, I'm done. So you guys have any further queries?
We Teachers Day, sir.
Sorry? Oh, thank you.
Very happy Teachers Day, sir.
Yeah, thank you. So if you don't have any queries, we can end it for today. Or you could ask. So this FPGA implementation is not compulsory for the course, but for you guys to know and to run and verify. If you have the facilities, then it will be very useful for you.
Sir, if you can get the power circuit module and signal conditioning circuit board, if you can purchase, then it will be useful. But I don't think it is available.
I don't think it's available actually. So you could also
that FPGA part we can get from the company.
Yes.
But but these two parts, if it is available from your side, yesterday we said this. I said the same thing with Teja Gola sir also. If it is available, then it will be useful, sir. It will make the course complete if you get that.
But actually, it's not in our hand. So
just yeah, sir. Just convey our concerns, sir, if it is possible to.
Yeah. Anyway, like you can make your own boards. There are like online softwares are there. The CAD tools are there.
Can we make all these in simulations? Like this real-time setup also, can we simulate?
Real time. You can simulate all these things, and there is some sort of software known as Simplist, in which you can also use the Verilog code, etc.
What's a Simscape?
Simplist software.
Spell, please.
This Simplist / Symmetrics. Okay. So in Symmetrics, you can include the Verilog code, but this is a paid software. Okay, it is not free.
Okay.
Yeah. Okay. This is very good software. Like, it is very accurate, gives close to the actual hardware things if properly modeled. That way. Yeah. So actually, what I was saying, those CAD tools are there. So there are online videos how to make a buck converter, boost converter, etc. So you can make it, and then you could get those components and solder them. Or instead, there are some. There's, I think, some jailed PCB, something I've heard, in which it might be costly, but you can get the board with the components already soldered, everything. So that provision also is there. So these things are there. So as you're actually in Rajesh, you're actually in the MTech, doing MTech, right? So you would have certain lab facilities, etc.
Yes, sir. This DSOs and everything I can access. This, but this buck converter, they are having, sir, but we can't access those inductors, everything.
See, no, in this board, we are using a small ready-made inductor. We're not used a custom inductor. So you could actually just use those readily available shielded inductors and make it. Capacitor also,
Sir,
if you
that thing for the laboratory experiment they are using. So everything is concealed, sir, inside a box. So we couldn't see.
Acha, that big box is there, huh? White transparent
Yes,
box.
for buck to boost.
Okay. Acha. So
If we have the physical components, can I solder them all to get this converter?
yeah, you can.
But I guess I require a lot of inputs.
Yeah,
like the value of everything. Like you are saying a lot about ADC and all are included in that.
You'll have to do ADC, DAC, resistor, inductor, capacitor, all that you'll have to do. One suggestion would be, see, all these Texas Instruments and other companies, they have what is, reference circuits of a buck converter, which they have made. Okay, they will be using their own controller. Instead, you can use the power stage, that is the inductor, capacitor, load, resistor, all that of those manufacturers, but a controller IC, you can use a FPGA. Because the FPGA will be used by you to generate the control signals for running your converter. So, like, basically what you need your inductor, capacitor, your switches, okay, your load resistor, then your input voltage. All right, that is required. Then you require gate drivers. Gate drivers are required for turning on the MOSFET. Then you require an ADC, DAC, their drivers you require. Further, you would also require a comparator, etc. So all these things, see, gate driver and all these circuits will be available in the reference design. These ADC, DAC, the drivers, the comparator, that you'll have to think and you'll have to design and make it. So in those reference designs, what will be available is which inductor they use, which capacitor they use, what is the part number, everything will be there. What is the value of the inductor? What is the rating of the capacitor? All that will be available for you. So you can use that and you can make it.
And how much does it roughly cost, sir, for the complete setup of this?
I don't have an accurate estimate of it because I
A rough
have
estimation.
rough also. I can't say because the PCB costs and all I do not know currently. I haven't dealt with that. Components like these resistors, SMD capacitors, they are not very costly. Yeah, those are not that costly. The ADC and DAC would be a bit expensive.
Sir, can we make this buck converter made in PCB in some websites where we get the components, this element 14, something like that?
See,
Can we?
JLPCB website you check, okay? There you make your PCB, okay, and then you tell them which and all components are there in the PCB, and then they will manufacture your PCB and they will solder the components and give it to you. Okay.
No, sir. What I'm asking is some ready-made default PCB for a buck converter or something that we can purchase.
Those are available, I think. Yeah. Those should be available. So ready-made buck converters, they are available.
Which should be exposed to like in a PCB board. Can we get a PCB board of a buck converter?
Yes. You could get a PCB. You could get a PCB board, okay, and it would be fully furnished with all the driver, gate driver, everything. All you need to give is you need to give the PWM signals. All you need to give is a PWM signals, and then it will work.
This we have to give from FPGA.
You have to give from FPGA. But you must make sure. But you must make sure that you have the provision for sensing the output voltage and sensing the inductor current so that you can run flow.
Yeah. So can you suggest any website from where we can get this PCB? Fabricated PCB of buck or boost? Okay, that would seem more. Sir, not immediately, sir. Yes. As